Okay, YouTube, this is my first video on multiple angle formulas in which we're going to look specifically at the double angle formulas. These formulas you can see listed thusly. I'll tell you what, for the most part, not many people memorize these unless they're true nerds like myself, or you use them on a daily basis. For the most part, we're just going to go refer to these, but I want you to notice in each particular instance, sine to u, cosine to u, tangent to u, we have a double angle. 2 times this angle u, and in every instance that it can be rewritten. So for instance, sine to u, it is an identity that it's the same thing as 2 sine u, cosine u. You'll notice that these are single angles. So the whole idea is that we can rewrite these double angles excuse me, as an expression containing single angles, which would be much more beneficial when we're either A, solving an equation, or B, trying to evaluate. We don't want to deal with double angles. Maybe we'll just cut it in half. So here's the idea. I will say this, at least for cosine, in terms of which of these 3 formulas you should use, or which of these 3 expressions of cosine to u, alternate expressions you should use, you're going to use the one that's most beneficial to you depending upon what information you've been given in the first place. So we are going to take a look at the use of a double angle formula in order to solve a multiple angle equation here. And so I'm looking at this equation. We say 2 cosine of a single x plus 2 sine of a 2x is equal to 0. So now, when you solve an equation, of course, the first thing you would want to do is set it equal to 0 and try to factor it. It seems that this is not factorable and that it doesn't have any greatest common factor, as well as the fact that, I have no squared things or reciprocal functions to do substitutions for. So I do notice, though, that we have a 2x here, a double angle. So what we're going to do is we're going to use our sine double angle formula. And I want to recognize, well, 2u in this particular case could be rewritten as 2 sine x cosine x. So what we have here is this. Using our double angle substitution, we have 2 cosine of x. Let me rewrite that there. 2 cosine of x plus 2 times, now in parentheses, we're going to make the substitution for sine 2x. It is 2 sine x times cosine of x. And so all together now, we say 4 sine x cosine x equals 0. And so now we know, or at least we identified that all of our angles are single angles. So with an expression like this, we have something plus something times something times something. We can factor out any common factors, which these all share a common factor of cosine, and they all share a factor of 2. So when we factor out this 2 cosine of x, we are left with this. We have 1 plus 2 sine of x, and this cosine is gone now, equals 0. So what this allows us to do is we could say, well, then either 2 cosine of x equals 0, or we have 1 plus 2 sine of x equals 0. So isolating these trig functions, that is, we'll divide everything by 2 over here. We get that the cosine of x equals 0, and also that if we took the cosine inverse of both sides, basically we say x is the angle that when we took the cosine of it, we got 0 for an answer. Also over here, if we were to subtract 1 and divide by 2, we would say then therefore we have the sine of x would be equal to negative 1 over a positive 2, and therefore that x would be the angle that when we took the sine of it, we got negative a half. Okay, so for the sake of time, I'm actually just going to pull out a unit circle here. I'm going to say, well, okay, where on the unit circle do we have x values or angle values for which cosine is equal to 0? And we say, well, cosine is equal to 0 at pi halves, and at 3 pi halves, at least on a 0 to 2 pi interval. So we have pi halves plus the period of cosine multiples, and 3 pi halves plus any multiple of its period there. So we say here are 2 solution values that we have for this equation. We also say that if we were to look at this, we say sine. Where is sine equal to negative a half at? We say sine values are y values. So we say if they're negative, they must be down here in 3 or 4. And we say sine is negative half at 210 degrees or 7 pi sixth. And also at, this other one has a 30-degree reference angle on it at 11 pi 6. So 7 pi 6 and 11 pi 6. So we have x, let me switch out colors here. X is 7 pi 6 plus multiples of sines period. And we say x is 11 pi 6 plus multiples of its period. So these are our solution values here. And just for the sake of actually visualizing this as well, why don't we graph this? So we have, as our initial expression, 2 cosine plus 2 sine 2x. So I'm going to pop this over to projector mode. We have 2 cosine x plus 2 sine 2x equaling 0. And we say, well, where does this equal a height of 0? So we say from 0 to 2 pi. Also, let's do this. X-axis will go by pi halves increments, pi divided by 2. You see this a little bit better. So from 0 to 2 pi, we say we had at pi halves, 7 pi 6, 3 pi halves, and 11 pi 6. So here's our pi halves, 3 pi halves, 7 pi 6, 11 pi 6, plus any multiple of its period on top of that. So that's how we could use a double angle formula in order to help us solve an equation where we have angles of different types. Cheers.